In this example, we're looking at linearly dependent, linearly independent vectors. And we did this in the worked example in the first section of this chapter. Now remember that when we did that originally, we looked at vectors being in their column form. So the idea was to look at three vectors. Now I'm just going to write down the vectors that we have. So A, which is 8i, 7j, 3k. I'm just writing them in a column form, just so you can remember how we did this previously. I is 1, j is -1, and k is 3. And for C, we've got I is 2, the coefficient of I is 2, j coefficient is 3, and -1. So what we did previously was we looked at the columns and we said, were there any vectors that were obviously not parallel? And you can see here, looking at B and C, you can see B and C are not parallel. And what that means is two things. That is, B is not some scalar multiple of C, where K is just a real number. And that also means that B and C are linearly independent vectors. So the way that we could then test dependence or linear independence was to use a method which was to look at the third vector, which here is A, and to see, okay, can A be constructed using these two other independent constructing blocks, I suppose. Think of it like Lego. You know, these are two blocks. Can you make A out of these two blocks, adding and subtracting them in some way? So we'd say that it's N times B plus M times C, where N and M are, some real numbers. That was what we did previously. So we're looking and saying that if this is satisfied, then A is not linearly, oops, that's not right, linearly independent. So that's what we're going to test. So we're going to do the same thing that we've done previously, but instead of using the columns, we're going to use the I, J's and K's explicitly. Now either way works, so if you're in an exam situation, use the way that works better for you. So with A, we're going to say again here, B and C are linearly independent, so we're going to test, can A be written as NB plus MC? And so we've got A, which is 8i plus 7j, oops, and I'll do this with my hats on there, equals n times b. Now b is all of this vector, I minus j plus 3k, and m times c, and c is all of this vector, 2i plus 3j minus k. So we now have 8i plus 7j plus 3k equals, and all I'm going to do here is expand this out. So I've got ni minus nj plus 3nk plus 2mi plus 3mj minus mk. And I'm just going to use the 3 equals signs here because I'm literally going to write this expression again. It's an I, just fix that up. I'm going to write this expression out again, but just factorise. So I'm going to combine all the i's together, so the n and the plus 2m, n plus 2m, the j's together, so that j there and that j. So we've got negative n, 3m minus n, there's the plus 3m minus n, and the k's together. We've got 3n minus m. So all I've done there is literally put the 3 equal signs because that is what that is. It's just been factorised. Okay, so we can now use that expression to help us solve the equation. So if we go to the next page, let's put this up in the corner there. Just give myself a bit of room. Okay, so now what we can do is we can equate because we know that I, j and k are linearly independent, we can equate the coefs of I, j and k. Because we know that in order for these two things to be equal, the coefficients of I would have to be equal, the coefficients of j would have to be equal, and the coefficients of k. So we've got three equations, only two unknowns, so this is what's called an overdetermined system. It means that you have more information than you need, which is always good. It's better than having less. And so we can use this information to help us solve. And the last one, 3 equals 3n, take m. Now in terms of solving this, there's a few ways you can go. Probably the easiest way is to do an elimination type method. So I'm just going to, what I'm going to do is I'm going to times this by 2. So we end up with 6 equals 6n, take 2m. And the reason I did that is now I've got these two m's that I can eliminate. So I'm going to do equation 1 and I'm going to add equation 3. So if I add those together, the left sides added together will give me 14. And then the right sides added together will give me 7n. And then the 2m and the negative 2m, they cancel. So from this I can now see, therefore, n equals 2. And let me just fix that. Doesn't look like an n. There we go. Okay, so n equals 2. And because now I know what n is, I can put that back in. So into 1, and you've got 8 equals 2 plus 2m. So 6 equals 2m. Therefore, m equals 3. So what that means is that hence a can be written as, and remember that we had this expression, this is what we were looking to show, test whether or not this is how a can be written. So we've got a equals nb plus mc, and we know now that n is 2 and m is 3. So you can actually construct a using b and c. So a is not linearly independent. I'll just put indept because it depends on b and c. So its construction depends on what b and c are, in which case it's not independent from those two other vectors, and as a result it's not linearly independent. Okay, so that's the idea with linear independence. So using this expression here, so finding two vectors that you believe are not parallel, okay, and then testing them by saying, can you construct the third vector using those two linearly independent vectors? Is there a solution to the equations? And here you can see there's a nice solution. Okay, so again with the next question, we've got here the same kind of thing, and so again we'll do the same sort of working. Here I'll just copy this so we can see this on the next page. The first question was saying, show that the vectors are linearly dependent, and we can see here that A is not a linearly independent vector, it depends on B and C. So we should finish off by saying the three vectors are linearly dependent. The next question is asking you to actually show that a set of vectors is linearly independent. So we know then already what's going to happen here. We're going to end up finding no solution in this case. So we'll have a go with this. We've got three vectors again. What you'll notice if you compare this question to the previous question, they're the same, they're the same. This is different just by this sign. So actually we can use the same method that we used previously. We're just going to have to change one of our equations. So I'm going to go, looking at this, you can see again that B and C are not parallel. Okay, so we're going to do the same thing again. We'll test this expression here, test that A equals NB plus MC. And the cool thing about this is because there's only one difference in the sign, I know that all I'm going to have to do with these equations is change here instead of having a minus K here, which contributed the minus M, okay, I've got a plus K. So this will become a plus M. So I can actually use all the same equations that I had previously, because the only thing that's changed, is that part, that third part. So 3 equations, and I now know, and I mean you can go through the whole thing again, but you'll see here the only thing that's changed is that plus there. Okay, so I've got 3 equations. My job now is to try and solve those 3 equations, and what I'm going to do is just move those onto the next page. Just move this over. So we're going to try and solve them now. Because we know that this is a prove it's linearly independent situation, we're going to then have to show that there is no solution. So I'm going to do a similar thing to what I did before, which is multiply 3 by -2 this time. So I'm going to do 3 times -2. So we'll get -6 equals -6n minus 2m. Now I'm going to add 1 and 3 just like I did before. So I end up with 8, and this time we're adding these two together, so we have 2 equals. We've got -6n plus n, so that's -5n, and then those disappear. So therefore n equals 2 on -5. Okay, then I can put that back into any of the equations here and try and figure out what m would have to be. So I've got, I'll just put a bracket around there, sub n equals 2 on -5 into, let's put it into 2. So we have 7 equals 3m minus 2 on -5, which is 3m plus 2/5. Multiply everything by 5. 7 times 5 is 35. 15m plus 2. So we have 33 equals 15m. Therefore, m equals 33 on 15. So not nice. Not nice answers. And then what we should do is then test that those solutions work. And actually, we really should have done that back here too, is to test the 2 and the 3 to make sure that they work. And you can see here in that previous example, 8 equals 2 plus 2 times 3. Oh yeah, that works. 7 equals 3 times 3 minus the 2, which was n. 9 minus 2, which is 7. That works. And then here, 6 equals 6 times 2 minus 2 times 3. 12 minus 6 equals 6. So that one worked. So you should do that actually to test it. So what we're going to do is test these n's and m's everywhere. 8 equals 2 on -5 plus 2 times m. Okay, 7 equals 3 times m. So m was 33 on 15 minus n. And the last one was 3, which was 3 equals 3n plus m. Not very nice numbers. So here we've got, I'll put everything here over 15. So we've got, this would be -6 over 15. This would be plus 66 on 15. So that would be 60 over 15. And 8 5s are 40. You can see there's a problem here. 8 5s are 40. 1 times 8 is 8, 9, 10, 11, 12. There's a problem with this because you can see that 15 times 8, which is what you want, you'd need to have 120 up here. So there's a problem there. And we could also test the others as well. So that's not going to be 8. We've got here top and bottom, divide the top and the bottom by 3. So you'd have 33 over 5 plus 2 over 5, which is 35 over 5. Well, that's 7, so that's cool. And here you've got, again, I'll make this over the top of 15. So that would be 6 times 3. 6 3s are 18. -18 over 15. 33 over 15. Should be 15 over 15, which is 1. And so those two are actually not satisfied. And as a result, we know that one of these, when we were doing our working here, must be inconsistent. So it doesn't allow us to actually solve this system. So there are, in fact, for this solution, or for this system, no solutions for this system of equations, and as a result of that, because there are no solutions, hence A cannot be written in a form that is n times b plus m times c. So those three vectors, or the set of vectors A, B and C, are all linearly independent vectors. So whenever you get no solution, it's completely correct. So you might have been working through this and think, uh-oh, it's not consistent. That's cool. That just means that there is no solution to this system, and that means that you cannot write one vector in terms of a linear combination of the others. They are linearly independent vectors.